Welcome to the Line Life Podcast. I'm Jeff Postlewaite, Senior Editor of T&D World, and today we're bringing you more stories of the grit, courage, and inspirational teamwork that it takes to be a line worker.
Thank you for tuning in to the Line Life Podcast. My name is Amy Fishbach, and I'm the field editor for T&D World magazine and the host of the Line Life Podcast. We recently celebrated our 100th episode of our podcast, and I invite you to join our Line Life podcast community at linelife.podbean.com. On this podcast, we celebrate the grit, courage, and inspirational teamwork that it takes to be a line worker. We offer 4 episodes a month, including new audio stories on the second and fourth Fridays of each month in our In Case You Missed It series, and interview-style episodes on the first and third Fridays of each month. If you know of a guest that we should feature on an upcoming episode, please make sure you email me at amyfishbach@gmail.com. I'd also love to hear from you if your utility is working on some interesting projects out in the field or using technology in an innovative way. For this episode in our In Case You Missed It series, we're featuring a topic that many of our line workers and troubleshooters often find themselves doing in the field, which is trying to get to the root of a problem. For this audio story, we're featuring the cover story of the April 2025 issue of T&D World's print magazine. This article is titled Mysterious Transformer Trips, Solving 3 Mysteries. This article was written by Mose Ramieh of CBS Field Services, and it's narrated by me, Amy Fishbach. Mysterious Transformer Trips, Solving 3 Mysteries. Transformer trips are a common problem, but the solution is sometimes not immediately obvious. A technician shares 3 stories from the field. Modern substation control and communications have revolutionized the ability to troubleshoot system faults and misoperations. Event fault records and documenting every input and output provide invaluable information to help answer the question, what happened? However, there are hundreds of thousands of systems with legacy equipment. These systems can present seemingly baffling challenges that could necessitate several attempts, test and try, to work through various scenarios to resolve the issue. Life in the electrical maintenance and acceptance testing business can throw strange situations your way. This is also true of my experience in the electrical testing business. These 3 stories occurred over the course of my career and might help you to be more efficient at identifying and correcting issues without all of the benefits of modern communication. These stories, focused on substation transformers, illustrate that regardless of the complexity of the situation and system, it is often the simplest of solutions that can be the hardest to find. 2 trips, 1 input. Springtime in Tennessee can present some variable weather. Freezing cold mornings and bathing suit temperatures in the afternoon are not uncommon. These temperature swings played an interesting role in the case of a mysterious transformer trip. Shortly after my 3rd cup of coffee, the call came from the plant engineer. "Get over here now! T1 just tripped off." Knowing little more than that, we headed to the customer's plants where we found a flurry of activity and questions regarding why transformer T1 had tripped offline. Physical inspection of the system noted no protective relay targets and an 86T transformer lockout relay operation. No protective relay operations? That's odd. Let's dig deeper and review the HMI event records. As we reviewed the event log, there was only one unrecognized item on the list, IN604. This input, IN106, is from the SEL 2411 that was installed to capture and communicate transformer trips and alarms. It was odd to note that the input was high on the event list and a short time later low. The input came in and then cleared. A review of the drawings showed that IN604 was tied to 2 fault conditions associated with the load tap changer, or LTC. Did someone grab the manual ITC crank handle, or was there a pressure relief operation? Noting that the LTC handle is behind a bolted cover and that no one had opened the cover, we turned our attention to testing the pressure relief device, or PRD. Tests and inspection proved that the switch operated properly and wasn't the source of the issue. With the mindset of better safe than sorry, we did some basic tests on the transformer and the LTC. All results were comparable to the previous maintenance results. After much discussion, a decision was made to energize the transformer. It was energized without issue and was left to soak overnight. The following morning, however, the transformer tripped again. Once again, the event log documented IN106 going high and then going low. There was no PRD operation, and no one had messed with the bolted cover that housed the LTC manual crank handle. All sorts of ideas began to fly about how the system must be misoperating. To leave no stone unturned, we opened the LTC handle cover to inspect the switch. Repeatedly moving and replacing the handle proved that the switch was doing its job. Handle out, IN106 went high. Handle in its holder, IN106 went low. More tests, more ideas, more head scratching. No smoking gun. We decided to turn it back on and let it soak overnight. The following morning, shortly after sunrise, another trip. Now I had enough information to see a pattern. What was causing a trip every morning shortly after sunrise? Then it dawned on me that perhaps the issue had something to do with the sun warming up the transformer from the overnight freezing temperatures. My theory was that there must be something wrong with the LTC handle or the PRD switch that only shows up in the transition from below freezing to above freezing. Fortunately, the weather continued to cooperate, and I had a chance to prove my theory. After all, the client wasn't going to be confident in the solution unless we could prove the theory. Early the following morning, our team showed up before sunrise, equipped with a hairdryer, not standard test equipment. We applied some heat to the LTC handle switch and noted that IN106 went high, but only for a moment. And then it went low and stayed low. As the switch warmed, moisture created a moment that caused the trip input to go high. With the theory confirmed, we were able to replace the switch and confidently bring the transformer online and restore the plant to normal service. Blame it on the rain. Another tricky example began with a call from a client that a transformer had tripped during a heavy rainstorm. A visual inspection found no protective differential or overcurrent relay targets, yet the 86T relay had been tripped. As in the previous example, you must investigate all the other protective device trips that could operate the relay in question. The list of those items that could operate an 86T is typically short and includes devices like PRDs and a sudden pressure relay, or SPR. It should be noted that both devices provide targets. SPRs are used in conjunction with a seal-in relay. This device, typically located in the transformer control cabinet, provides a target and seals in the trip so that manual resetting is required. PRDs will flip up a yellow flag if they lift, assuming the flag isn't missing or broken. The PRD switch is a latching device that also requires a manual reset. The PRD isn't as easy to access as is typically located on the top of the transformer, and the switch is located under the bell housing of the device. So how could an unflagged PRD or SPR operate the 86T relay, and what's the weather got to do with it? Simply put, damaged wiring, insulation, and/or device connectors, combined with water intrusion, can create a sufficient low-resistance path to complete the trip circuit. This failure mode is almost always related to the PRD, since it operates on one normally open contact going closed. In comparison, the SPR has two contacts, one open and one closed, and both sets must change state to trigger an operation in the seal-in unit. A mind of its own. In this final story, a transformer tripped on an 86T relay operation that opened the SF6 breaker ahead of the transformer and tripped the secondary main in a separate E-house. Keeping with the theme, the strange part was no targets to help explain what caused the operation. A review of the drawing showed several items that could operate the 86T relay: transformer differentials, low gas pressure in the SF6 breaker, and the sudden pressure relay. We verified all the trips, and they all appeared to be operating and targeting properly. We tested the transformer, and all results, including a DGA, came back acceptable. With no smoking gun, the decision was made to turn the transformer back on and load it, which was all done successfully and without any drama. The transformer serviced the plant fine for about 18 hours. Then, without warning, it tripped by the 86T relay with no targets on the protective devices. What's going on here? It's not the SF6 gas breaker, low pressure trip, or sudden pressure relay. It must be the HU model relays, but there are no targets. So we tested the relays and verified that the targets operated. Everything on the relays worked perfectly. We energized the transformer and loaded it again without any issues. The transformer carried the plant for about 18 hours, and then, once again, the 86T rolled and with no targets. The question now was what changed in the plant. Fortunately, one of the engineers spoke up and shared that both of the previous 2 trips occurred when they were attempting to start a large HP motor. The transformer system was fine when lightly loaded. Only when a full load was being added did the problem reveal itself. Many readers know that it takes a minimum load, usually 30%, before a transformer differential will operate. Now that the relays have tested fine, what's the problem? With today's modern relays, troubleshooting a differential trip is so easy a caveman could do it. Older systems with an electromechanical differential relay like HUs represented a greater challenge. Our plan to identify the issue required us to energize and load the transformer with the differential relay trips pulled or opened. Want to measure current magnitude or compare your phase angles on a system with HU relays? You need a current thief and a phase angle meter. Fortunately, we had the necessary equipment. Start with measuring the primary and secondary current into the relay. In most cases, you must do the math to compare the primary current magnitude to that of the secondary. In our case, there was no secondary current. Now, it wasn't 0, but it wasn't anywhere close to the amount we were expecting. With this new piece of information, our investigation turned to the secondary main current transformers, or CTs. When we walked into the E-house, we could hear the audible groan of CTs that are in saturation because of an open CT secondary circuit. More specifically, in this case, an extremely high burden resistance. After making the system electrically safe, the CT secondaries to the remote E-house were tested, and it was confirmed that they had failed in the underground conduit. After pulling and landing new CT secondary wires, the transformer was successfully returned to service. Now, I hope you're asking yourself, so why didn't the differential relays target? It was a legitimate differential fault because of the lack of secondary current input. As it turned out, this issue goes all the way back to the improper and incomplete commissioning of the system when installed a decade earlier. The relay targets were set to the 2.0 amp tap, which is an issue in this application because the current necessary to operate the 86T relay is much less than 2 amps. For that reason, no targets dropped when the HU relays operated the 86T relay. After adjusting the relay targets to 0.2 amps and testing the system, we verified that if the HU relay operated and tripped the 86T relay, the targets would operate on all 3 relays. Conclusion. Transformer trips are a common problem faced by engineers and technicians in the field. They can be caused by various factors, including weather conditions, faulty wiring, damaged insulation, and malfunctioning protective devices. In many cases, identifying the root cause of the problem can be a challenging task that requires a thorough investigation of all possible scenarios. As demonstrated by these examples, the process of troubleshooting transformer trips involves a combination of technical expertise, attention to detail, and persistence, lots of it. Editor's note: this article was provided by the International Electrical Testing Association. NETA was formed in 1972 to establish uniform testing procedures for electrical equipment and systems. Mose Ramieh is Vice President of Business Development at CBS Field Services. A former Navy man, Texas Longhorn, vlogger, CrossFit enthusiast, and slow cigar smoking champion, Ramieh has been in the electrical testing industry for more than 25 years. He is a Level 4 NETA certified technician with the eye for simplicity and using the KISS principle in the execution of acceptance and maintenance testing. Over the years, Ramieh has held positions ranging from field service technician, operations, sales, and business development to company owner. Thank you so much for listening to the Line Life podcast. And again, please visit linelife.podbean.com to subscribe and follow the Line Life podcast so you're notified when new episodes are available. Thanks again for listening.
This episode of the Line Life podcast was written, recorded, and edited by Amy Fishbach. It was produced by Jeff Postlewaite. That's me. To listen to past episodes, visit www.tdworld.com/podcasts or find us at Podbean. You could also drop us a voice memo or message at linelifepodcast@gmail.com with your comments on this episode. We'd love to hear from you. Please follow this show on Podbean or your favorite podcasting app to be updated when new episodes are released. Thank you for listening.